The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
And this is a question based on where we left off on Wednesday. We were talking about Coulomb's force law to describe the interaction between two particles. And good job, most of you got this correct. So what we're looking at here is the force when we have two charged particles, one positive, one negative. Here, the nucleus and an electron. So I know this is a simple example, and I can see everyone pretty much got it right, and probably those that didn't actually made some sort of clicker error is my guess. But I wanted to use this to point out that in this class, in general, anytime you see an equation to explain a certain phenomenon, such as here looking at force, it's a good idea to check yourself by first plugging it into the actual equation. So you could plug in infinity in this equation here, and what you would see is, of course, the force, if you just solve the math problem, goes to 0. But you can also look at it qualitatively. So if you think about the force between the electron and the proton, you could just qualitatively think about what's happening. If they're close together, there's a certain force. They're attracted because they have opposite charges. But as that gets further and further away, that force is going to get smaller and smaller, and eventually the force is going to approach 0. So it's a good kind of mental check as we go through this course to remember every time there's an equation, usually there's a very good reason for that equation, and you can go ahead and just use your qualitative knowledge. You don't have to just always stick with the math to check and justify your answers. So we can get started with today's lecture notes. And as I mentioned, we left off, and as we started back here, to describe the atom and how the atom holds together the nucleus and the electron using classical mechanics. And today we'll finish that discussion and, of course, point out actually the failure of classical mechanics to appropriately describe what's going on in an atom. So then we'll get to turn to a new kind of mechanics, or quantum mechanics, which will, in fact, be able to describe what's happening on this very, very small size scale. So on the atomic size scale, in the order of nanometers or angstroms, very small particles. And the reason that quantum mechanics is going to work where classical mechanics fails is that classical mechanics did not take into account the fact that matter has both wave-like and particle-like properties, and light has both wave-like and particle-like properties. So we'll take a little bit of a step back after we introduce quantum mechanics and talk about light as a wave and the characteristic of waves, and then light as a particle. And one example of this is in the photoelectric effect. So we just talked about the force law to describe the interaction between a proton and an electron. You told me that when the distance went to infinity, the force went to 0. What happens instead when the distance goes to 0? What happens to the force? Yeah, so the force actually goes to infinity, and specifically, it goes to negative infinity. Infinity is the force when we're thinking about it in our brains. Negative infinity is when we actually plug it into the equation here. And the reason is the convention that the negative sign is just telling us the direction that the force is coming together instead of pushing apart. So we can use Coulomb's force law to think about the force between these two particles. And it does that. It tells us the force is a function of that distance. But what it does not tell us, which if we're trying to describe an atom we really want to know, is what happens to the distance as time passes. So r is a function of time. But luckily for us, there's a classical equation of motion that will, in fact, describe how the electron and nucleus change position or change their radius as a function of time. So does anyone know which classical law of motion that would be? Yep. So it's going to be Newton's second law, force equals mass times acceleration. Those of you that are quick page turners have a little one-up on answering that. And that tells us force as a function of acceleration. We want to know it, though, as a function of radius. So we can just take the first derivative and get ourselves to velocity. So force is equal to mass times dv dt. But of course, we want to go all the way to distance, so we take the second derivative, and we have this equation for force here. And what we can do in order to bring the two equations together is to plug in the Coulomb force law right here. So now we have our Coulomb force law all plugged in here, and we have this differential equation that we could solve if we wanted to figure out what the force was at different times t or at different positions of r. So all of you will have the opportunity to solve differential equations in your math courses here. We won't do it in this chemistry course. In later chemistry courses, you'll also get to solve differential equations. But instead, in this chemistry course, I will just tell you the solutions to differential equations. And what we can do is we can start with some initial value of r. And here I write r being 10 angstroms. That's a good approximation when we're talking about atoms, because that's about the size of an atom. So let's say we start off at the distance being 10 angstroms. We can plug that into this differential equation that we'll have and solve it. And what we find out is that r actually goes to 0 at a time that's equal to 10 to the negative 10 seconds. So let's think qualitatively for a second about what that means, or what the real meaning of that is. What that is telling us is that according to Newtonian mechanics and Coulomb's force law, is that the electron should actually plummet into the nucleus in 0.1 nanoseconds. So we have a little bit of a problem here. And the problem that we have is that what we're figuring out mathematically is not exactly matching up with what we're observing experimentally. And in fact, it's often kind of difficult to experimentally test your mathematical predictions. A lot of people spend many, many years testing one single mathematical prediction. But I think all of us right now can probably test this prediction right here. And we're observing that, in fact, all of us and all the atoms we can see are not immediately collapsing in less than a nanosecond. So just if you can take what I'm saying for a moment right now, that in fact this should collapse in this very small time frame, we have to see that there's a problem with one of these two things, either the Coulomb force law or Newtonian mechanics. So what do you guys think is probably the issue here? So it's Newtonian mechanics. And the reason for this is because Newtonian mechanics does not work on this very, very small size scale. As we said, Newtonian mechanics does work in most cases. It does work when we're discussing things that we can see. It does work even on things that are too small to measure. But once we get to the atomic size scale, what happens is we need to be taking into account the fact that matter has these wave-like properties. And we'll learn more about that later, but essentially classical mechanics does not take that into account at all. So we need a new kind of mechanics, which is quantum mechanics, which will accurately explain the behavior of molecules on this small scale.